In this video, we will cover systematic nomenclature for designating configuration of chiral compounds. So that's Cahn-Ingold-Prelog nomenclature. To designate configuration of chiral compounds, we use systematic nomenclature. It's also called Cahn-Ingold-Prelog nomenclature, after the chemists who introduced that nomenclature, and also we call it RS system of nomenclature, because two enantiomers are designated as R and S. This is system of nomenclature that you have already encountered when naming isomers of alkenes, EZ nomenclature. It's the same nomenclature introduced by the same scientists and follows the same rules. While in an alkene, each carbon had two different substituents, and all you need to do was to determine which of the two substituents had higher priority. Now each chirality center has four different substituents. And now you have to order those four substituents in the order of priorities from 1 through 4. Rules are the same. It is the atomic number of the atom directly bonded to chirality center that matters. So you're not looking at the entire group, but only at the atom directly bonded to chirality center. So here we have an example of 1-chloroethanol. So chirality center is carbon 1, and it has four different substituents. We look at atom from each substituent directly bonded to chirality center. So starting at the top clockwise, we have oxygen, atomic number of 8, then hydrogen, atomic number 1, chlorine, atomic number 17, and carbon, atomic number of 6. So in the order of priorities shown on the right, chlorine has the highest priority, oxygen second highest, carbon third highest, and hydrogen fourth highest. So that's how we have ordered the four substituents in the order of decreasing priorities from 1 through 4. Now, if two atoms from substituents are the same, then we have a tie, and we have to follow in each chain path of the highest priority until we encounter the difference. You have already seen that before, and here is another exercise. So here, chirality center, carbon is not shown, it's shown as a line formula, but chirality center is indicated as with an asterisk. And so we have two different substituents, clearly two different substituents, chlorine and hydrogen. So there is no doubt about them. But then we have two chains, two carbon chains, and we have two carbons that are attached to chirality center. So that's a tie. So we can easily assign priority 1 to chlorine and priority 4 to hydrogen, because chlorine obviously has the highest atomic number and hydrogen the lowest. But with these two larger chains, question is which has priority 2, which has priority 3. So two carbons have the same priority. We follow in each chain path of the highest priority. So to each carbon, the atom of the highest priority that is attached to each carbon is carbon, another carbon. And so we again have a tie. So second atom of the highest priority in each chain is another carbon atom. So again, we have a tie. Now we look at that second carbon, and what is the atom of the highest priority attached to those carbons? And now finally we have a difference. It's chlorine versus fluorine. So chlorine has higher priority than fluorine, so the entire chain, so the entire chlorine containing chain will be higher priority. It will have priority 2, while fluorine containing chain will have priority 3. And now that we have designated priorities 1 through 4, good idea is to make a model, although very soon you will be able to determine RS configuration without a model. So you make a model and you place substituent 4 away from you, so that you look at the chirality center in such a way that substituent 4 is eclipsed by the chiral atom, so that you don't see substituent 4. Then you will see only substituents 1, 2, and 3. And then if those three substituents make 1, 2, 3 order counterclockwise array, then that's designated as S enantiomer, after Latin sinister or S. If the three substituents in the order 1, 2, 3 make clockwise array, then that's designated as R, from Latin rectus or right. The easy way to memorize this is that if you imagine that those three substituents are 3 points on steering wheel of a car, then counterclockwise turn of a steering wheel will result in left turn of a car, and clockwise will result in right turn of a car. And so right turn is labeled as R, so that's very easy to memorize. So from this example, you can see that lowest priority substituent, priority 4, has to point away from you. Ideally, you wouldn't see it. But as long as it points away from you, it's behind the plane of the drawing, you can ignore it. Which means that in a case of compound that is represented in a perspective drawing, all that is necessary is for substituent 4 to be on a dashed bond, to point away from you. And then you can ignore it and simply look what is the array that substituents with priorities 1, 2, and 3 make. And so here we have example of 1-chloroethanol. Substituent 4, hydrogen, is away from you, so you can ignore it. And so that's counterclockwise array, so that's S1-chloroethanol. And note how we designate that. So S is capital S in italics in print, in parentheses, and before the name of the compound. If we have a Fischer projection formula, then, as you know, vertical bonds in a Fischer projection formula point away from viewer. So lowest priority substituent has to be on a vertical bond. And as long as it's on a vertical bond, then we can ignore it. So in this case, you can determine priorities yourself. Oxygen has priority 1. Carbon that has carbonyl group CHO attached to it has priority 2, and methyl group priority 3. So that's counterclockwise array. So this is S2-hydroxypropanol. At this time, you don't know how to name aldehydes, so you wouldn't know that this is propanol, but you should be able now to designate this as S enantiomer. When determining the order of priorities, you may be dealing with substituents that have multiple bonds, and so you may need to introduce virtual bonds and virtual atoms. And here are some rules how to do it. Just to remind you, we already covered that, so to remind you of the rules. So you should redraw Lewis structure of the substituent and represent all of the bonds as a single bonds. So convert even multiple bonds into single bonds. It should be complete structure, including all the atoms and all the bonds. And then add virtual bonds to satisfy valence requirements of each atom, not just carbon, but each atom. So if carbon had a total of 4 bonds, that is total of sigma and pi bonds, in the original substituent, it should have now 4 single bonds. Oxygen should have 2 single bonds, and so on. Nitrogen, 3 single bonds, and so on. And then those new bonds have nothing at the end. They are so-called dangling bonds, virtual bonds or dangling bonds. So at the end of each of that dangling bond, place a virtual atom. It's the atom that is at the other end of the multiple bond. And finally, this is not necessarily related to virtual atoms. Among the isotopes of an element, heavier isotope has higher priority. Obviously, isotopes have same atomic number, so heavier isotope has higher priority. Besides knowing how to introduce virtual bonds and virtual atoms, you may also need to transform a formula. I already mentioned that lower priority substituent must be pointing away from the viewer. So to place lowest priority substituent in such position, you may have to transform Fischer projection or perspective drawing so that you can determine configuration properly. So you need to know which transformations of a particular formula are allowed and which are not. So one of the allowed and important allowed transformations of Fischer projection formulas is exchange of the position of 2 substituents in pairs. So positions of both pairs must be exchanged simultaneously. That also means that rotation by 180 degrees is allowed because that's also exchange of 2 substituents in pairs, top and bottom, and left and right. If you exchange them simultaneously, that's 180 degrees rotation. Now, exchange of only one pair of substituents results in representation of enantiomer of the original molecule. And of course, that's not allowed. But if you exchange one pair of substituents, you get enantiomer, and then you exchange the other pair of the substituent, that's enantiomer of the enantiomer, or the original molecule. So that's allowed. And so here is shown how to do it. So the middle is S2-chlorobutane, and you can exchange two pairs, as indicated by arrows, positions of methyl group and hydrogen, and chlorine and ethyl group, and you obtain representation of the same molecule on the left. Or you can do 180 degrees rotation, and you obtain representation of the same molecule shown on the right. Another transformation that is allowed is exchange of the positions of three substituents, any three substituents, either clockwise or counterclockwise, while keeping the fourth substituent in the original position. That actually is rotation about a single bond, just on the plane of paper in a formula. So this transformation amounts to rotation about a single bond. So here is one example where three substituents, bromine, methyl group, and hydrogen, are rotated clockwise, while remaining large substituent, ether substituent, is left in place. And still we end up with the same enantiomer. There are some transformations of Fischer projection formulas that are not allowed. What is not allowed are transformations that convert one enantiomer into another. And that would be exchange of position of only one pair of substituents. So if you flip only one pair of substituents, you get an enantiomer. And of course you need to know that in case you want to draw an enantiomer on purpose, that's how you do it. You exchange only one pair of substituents. Another very important transformation that is not allowed, and that's a mistake that is very easy to make, is rotation of molecule by 90 degrees. Fischer projections use solid lines to indicate positions of the substituents, with horizontal bonds having particular meaning. They indicate that substituents are projecting towards you, remember bow tie convention, and vertical, that substituents are projecting away from you or are below the plane. So rotation by 90 degrees actually inverts those substituents, flips those substituents. And of course, that's not allowed. Rotation by 90 degrees would result in representation of the enantiomer. So you can see that from this example. So as a conclusion, Fischer projections may be rotated by 180 degrees in the plane of the paper. And that means either actual rotation by 180 degrees or flipping two pairs of substituents simultaneously. But they can never be removed from the plane of the paper. And removing them from the plane of the paper means flipping only one pair of the substituents or rotation by 90 degrees. Even though that may not be obvious, that's actually what those not allowed transformations do. Or to put it another way, allowed transformations amount to a rotation of the molecule, while not allowed transformations amount to breaking of the bonds. Now we are going to look at allowed transformations of perspective formulas, and they are very similar to Fischer projections. And in fact, because in perspective formulas we indicate stereochemistry, we indicate which substituents are up or down or in the plane of the drawing, there is a little bit more flexibility in manipulating them. So we are allowed to exchange positions of two substituents in pairs or rotation by 180 degrees. Of course, both pairs must be exchanged simultaneously. So again, we have a formula in the middle, R3-iodohexane, and exchange of two pairs as indicated by arrows results in formula on the left. It's the same enantiomer. And rotation by 180, again, same enantiomer. Also, exchange of the positions of three substituents clockwise or counterclockwise while keeping fourth substituent in original position is allowed. That's again rotation about a single bond. And from perspective drawing, actually it may be obvious that this is rotation about a single bond. Rotation of molecule by 90 degrees is actually allowed. In Fischer projection it was not allowed, but here it is allowed because we are indicating which substituents are above, which are below the plane of the drawing, which are in the plane of the drawing. So this is allowed transformation as long as you draw stereochemistry properly. Transformations of perspective formulas that are not allowed are, as expected, those that would convert enantiomer into opposite enantiomer, and that means exchange of positions of only one pair of substituents. So if you flip only one pair of substituents, you end up with enantiomer. Again, this is important to know, both to avoid it as a mistake, but also if you want to draw an enantiomer, that's how you draw an enantiomer. Sometimes when we study reactions, for example, determining reaction mechanisms, particularly in biochemistry, it is important to use chiral methyl group. But since methyl group contains 3 hydrogens bonded to carbon, at first glance it appears that it's impossible to have chiral methyl group. How can we have chiral methyl group when there are 3 hydrogens attached to it? But of course, hydrogens have isotopes, and as it happens, there are 3 isotopes of hydrogen: protium, deuterium, and tritium. And so if we synthesize methyl group that contains one of each isomers, then that methyl group could be chiral. And so here are representations of chiral methyl group, 2 enantiomers. So methyl group attached to the rest of the molecule represented as R. So on the left we have perspective drawings of 2 enantiomers, and on the right Fischer drawings of 2 enantiomers of methyl group. The absolute configuration of a chiral molecule is the actual arrangement of atoms at the chirality center. So to know the absolute configuration of a compound means that we are able to assign particular formula to it, to each enantiomer. So, for example, if we have 2 bottles of 2-butanol, that's chiral compound, we have 2 enantiomers. One enantiomer rotates plane of polarized light to the right, one to the left. So one is plus, one is minus. How do we know which one is S and which one is R? Sign of rotation is not related to absolute configuration, and in fact it may change depending on the wavelength of light we use and conditions under which we determine sign of rotation and magnitude. So until about mid-20th century, absolute configurations were not known. Only relative configurations were known. And it was even believed that we will never know, that it's not possible to know something like that. Now, early in the 20th century, because we had to designate enantiomers some way, in one way or the other, Rozanov, chemist from New York University, introduced a convention that was based on glyceraldehyde. And so Rozanov used glyceraldehyde, very simple chiral compound, and at that time RS convention was not in use. It was not introduced yet. It was DL convention that was used. So in this particular compound, D corresponds to R and L to S. That's not always the case, just in this case, that's how it happens. So Rozanov basically made a guess. So he designated glyceraldehyde, where in Fischer projection OH group was on the right as D-glyceraldehyde, and one where OH group was on the left as L-glyceraldehyde. At the same time, Emil Fischer actually had some dispute with Rozanov and didn't agree with that, but he actually made the guess that D-glucose had a formula as shown here, and L-glucose was the opposite enantiomer. So he designated that as D-glucose based on the configuration of the bottom chirality center in the Fischer projection. So in red squares are OH groups, H and OH, that are responsible for each convention. Rozanov made the guess. He had 50-50 chance of getting it right or wrong. And it wasn't known until 1951 whether he was right or wrong. And of course, all of the other chiral compounds through a series of reactions were related to configuration of D and L glyceraldehyde, and so there what we would think are absolute configurations were determined. It's just that we didn't know whether absolute configurations were correct or not. In 1951, a group of Dutch chemists led by Bivoyet were able to determine the absolute configuration of sodium rubidium tartarate. They were using some special technique called anomalous X-ray dispersion, and they were able to distinguish one enantiomer from the other. And they showed that Rozanov and Fischer guesses were actually right, and so they were correct, that they guessed right. So D-glyceraldehyde, or as he puts it now, R-glyceraldehyde, really has this formula where OH group is on the right. And D-glucose really has the formula where this last OH group, last chirality center, is on the right. So that's absolute configuration, when we can tell which enantiomer actually has which formula. So this completes our study of RS nomenclature, and next we are going to do some exercises.